How's it going, guys? Today I'm going to talk about dynamic memory allocation, which is a powerful tool and concept inside programming. So this kind of completes the gap between C and higher level languages like Java, where you can do dynamic allocation using the new keyword. However, unlike Java, C doesn't have a garbage collector, and C kind of gives you fine-grained control of your program. So this might cause some serious bugs. And again, these bugs may have serious consequences, so stay until the end to see how you can prevent these bugs from happening or detect them. So I've created this file called sus.c, and it's meant to be a suspicious file with a bunch of these bugs, but I'll just show you kind of how hard it is to spot them at first glance. We just have a function here doing things, processing numbers, and then we have a main function that, again, also does stuff. At first glance, you might think there's nothing wrong with this program, but there are a lot of things wrong with this program, and I'll show you in this video kind of how to spot them. First, let me just go over what malloc is, because malloc is actually the library call that is responsible for telling the operating system to create memory. Notice that this is different from the stack-based allocation because size here is actually a parameter, which means that the program doesn't actually know how much it wants until it actually is starting to run. So for example, you might get the size as a user input or from the network or from a database. All of these can change, so we don't really know how much to give it until it runs. That's where malloc comes in, because malloc will say, I don't care how much you give me, I'm just going to tell the operating system how much you want. And if you're a success, then you get a pointer to kind of your rented memory space. Otherwise, you get null, which means the operating system won't rent memory to you, and therefore memory allocation failed. So I'm going to use this renting analogy because it kind of will illustrate some of the bugs that will occur. First, let's just run it and see what's going on. We're going to compile it first, gcc-w-g. And by the way, I'm turning warnings off on purpose because otherwise that kind of ruins some things. But don't run it with -w. But I'm doing it for this video so that you can see the address sanitizer. So -w-g and then sus.c. And then we will just compile it and run it now. So now we get the segmentation fault core dump. This is a very famous error. There are memes on it on the internet because this doesn't tell you anything. What does this mean? We don't know. All we know is that something happened to this program. It basically crashed out. And this operating system is like, no, you can't continue. Something happened. You're trying something that is illegal. And I'm going to have to stop you right there and terminate you. But we don't know what it tried, what it did. So again, not useful. However, we have this tool called Address Sanitizer, and it can help us detect why this is segfaulting. So let's just compile it again. By the way, the warning will also show you why, but again, we're leaving warnings out of this because they're kind of easy and defeat the point of Address Sanitizer. So we're just going to compile with f sanitize equals address. So this will enable Address Sanitizer, and then it will tell us why it is segfaulting. So once we run this executable again, by the way, before I run this, I'll just show you kind of quickly what Address Sanitizer is doing. So there's a nifty tool called object dump where it kind of shows you the disassembled version. So I'm just going to run it with actually let me do the man pages because I can't remember if it's capital or lowercase. So yeah, capital is disassemble all. We don't actually let's do that because I kind of want you guys to see what it's trying to do here. So let's just do capital D. So we're disassembling the entire linked thing, and we want to see if you notice. It kind of, so if we scroll up here, it kind of injects. Okay, maybe disassembling all is a bit too much. All right, let's change it to lowercase d. Notice these asan. So asan is address sanitizer. So it injects assembly calls into our program to kind of see and manipulate stuff, which is pretty cool. So it's kind of modified our executable and mutated it so that it can report stuff, because otherwise it can't really tell what's going on without actually being inside the assembly. So you can see there's call to the address sanitizer report. And yeah, so if you just ever wondered how the address sanitizer detects these interesting things, that is how they do it. They just directly inject instructions inside to your program. But yeah, now we know our program is mutated with address sanitizer instructions. We can actually run it, and it will show us what it thinks. So we get an error, and this error, address sanitizer will tell us first, heap use after free This doesn't address the seg fault, however, because it's basically scanning through the assembly instructions, and we have this bug right here, and this comes before that assembly instruction that causes the seg fault. So what I'm going to do real quick is I'm going to actually show you how to spy it manually, and I'm going to fix it, and then I'll let Address Sanitizer spy it again, because basically it detected the heap use after free in this function, but the seg fault actually happens in main, which is after this function. So the seg fault happens here, and the reason why is because it's accessing a very large address. In fact, some may call it comically large. So that's why the operating system is like, no, that's reserved for the kernel or some other process. Therefore, you can't have it. So I'm just going to quickly set it to 1 for a second, and then therefore it will kind of allow it to run again. Basically, now what we're going to do is going to fix this heap use after free address first, because again, it didn't get to the seg fault just yet. So to do that, we're going to go back, and first let's just interpret this error for a second. So in the stack trace, we're looking at this thread T0. So this is the stack frame. It happened here, sus line 30, and basically what this says is, remember how we're renting stuff from the operating system? Now we're basically saying when we free stuff, we're returning the keys kind of to the operating system. We're saying we're done using this memory, you can have it back. But then we're using it again. So we're like, actually, hold up, I changed my mind, can I use it again? And of course, this will cause buggy behavior because the operating system may not let you use it again, or it may have done other stuff with it. So down here is where it happened. So notice how we've created a temp allocation, then we do stuff with it, we free temp, but then we're trying to access temp again, and this will cause an error. So the logical fix is just to move this before free, because after you free it, it's for all intents and purposes, it's just basically done. Like, you can't access it again. Some people actually, for good practice, may just set temp to null so that you're forced to get a seg fault. But yeah, that is how you fix that error. So when we compile it and run it again, let's just run it again, take that out. We will get a different error this time, but that error will be gone. So this error is a heap buffer overflow. Now this just means that we've kind of accessed something. So we reserved a location, a buffer that we kind of want to do stuff with. So we rented a space, but we kind of went to our neighbor and we kind of messed with their stuff. That's what the heap buffer overflow is. We overflowed our space, we went to some other space, and that's not allowed. So where does this occur? This occurs in sus 37, and I know there's a frame above this, but this is in some intrinsics inside the sanitizer, so I'm ignoring that. So just look at the stuff that you wrote, and that's 37. So let's go there really quickly, and let's see why it overflowed. So we allocated a 2-byte buffer. Keep in mind, malloc takes in a size specified in bytes. So, and by the way, size of character, so characters are 1 byte, so 2 times 1 is 2 bytes. But then we're trying to copy in this gigantic mess of a string into this buffer, and these 2 bytes get copied in nice and well, but then stuff starts overflowing to other things because this is way bigger than the 2 bytes we allocated. So the correct solution to fixing this bug is just to give it more space. So instead of asking for a 2-byte buffer and then kind of overflowing your rented area, just ask the operating system for more. So in this case, I believe it's like 21 characters, so we're just going to give it like 22. And then when we run it, first compile it to get a new executable, then run it. You can see this error is gone. So we don't have this weird heap buffer overflow, but we do have another error. Again, I told you there's a lot of errors inside this. First, just notice that it actually managed to run the program. So it ran our string, starting the program, sum of numbers, temporary value. It printed the buffer because we gave it space, program finished. But then Address Sanitizer is like, okay, your program is finished, but I've detected something that you forgot to do. And that, of course, is a memory leak. And where is this memory leak? Direct leak of 20 bytes. So these 20 bytes in one object here for line 14, it's just leaked away, and that's bad. So let's see why. Let's just go to this line here. So 14, yes, this is our initial allocation where we allocate some numbers, but the issue is we never freed it. So we kind of told the operating system we want to rent this space, but then those 20 bytes, they never got freed. So the operating system is like, what do you want to do with it? Because what happens is, remember, this is a local pointer, and when this pointer gets kind of popped off the stack, it's just gone. So you just have like a rented space. The operating system still thinks that it's reserved, but you don't know how to get to it anymore. And therefore, it's just like again, it leaked. Something leaked away out of your control. The solution to this is just to free it. But you gotta be careful because otherwise you'll get that heap use after free again. So we gotta find the last place we use numbers and then free it after. So it seems like this is the last place where we calculate the sum. So just after this, we do free numbers. And then when we run this again, you'll see Address Sanitizer has no errors, no complaints. Our program is safe. But I do want to go back to that seg fault because now it should be able to detect that. And since we address everything, so let's give it a very large value again. So this is definitely accessing outside our memory space. When we compile it with Address Sanitizer again and run it, and oh, I'm surprised. I guess okay. So I think so that's not large enough because the stack actually is like I believe 8 megabytes. So that's not enough. This is only what, like 1 megabyte? Yeah. So we need to make it way larger. So actually, I'm gonna switch to hex because we are going to make this buffer overflow really large. And then when we do this time, yeah, it will seg fault because the stack size is 8 megabytes, I believe, default in Linux. And this time we put in like however gigabytes or something, and that definitely causes a violation. So it says a seg fault, it returns a daily signal on an unknown address, and the Address Sanitizer actually gives you hints, which is very nice. So it says it's caused by a read memory access violation, and the hint is this fault was caused by a dereference of a high value address. See register below. And it gives us the stack trace where it is, and it kind of tells you, like it tells you how to fix it. It dereferenced of a high value address. So if we go into this again, and then we go down there, this is that high address that I gave it, which is way higher than any stack can handle. The solution to this, of course, is just to make it 11 because we want to put it down here. We want to put it here. So I'm just gonna save it, and before I do, pause the video and see if you can, in the comments, predict if there's a error with this or if Address Sanitizer will be fine with this, and if there is an error, what is the error and why. So see if you've just been following along. And yeah, let's compile it and run it. So we will compile with Address Sanitizer, and then we will run it. And another issue happened. So if you guessed that, and if you guess that it's a stack buffer overflow, you'd be correct. And in this case, again, it tells you that in this frame, this buffer overflowed at this offset. And this is obviously an issue because we told it to allocate 10 bytes, but we're accessing the 11th byte, and that is, of course, outside that range. And by the way, the stuff down here is for more advanced things because there are ways to actually use buffer overflows to your advantage. And that's called buffer overflow attack. So hackers actually use this to kind of exploit your program. That's why it gives you stuff like the shadow bytes and then even the red zone and then stuff that, again, it's just more advanced that I don't think I will cover in this video, but just know that all of this is very useful if you're trying to kind of catch an exploit happening. And by the way, if I don't run it with Address Sanitizer, so like let's remove this flag for a second, the operating system will also detect this as well. Notice how it says stack smashing detected. We're trying to do something to the stack that is pretty bad. So that's why it immediately terminated our program to prevent anything bad from happening. And the reason why it does this is because we are actually accessing some areas of the stack. So for example, the end of the stack where the return address is, and that has a stack canary, which is just a value that the operating system checks to make sure it doesn't get overridden. And if it does, it indicates that some sort of malware exploit has occurred. So again, this is very useful in terms of exploiting your program if hackers want to kind of get their way and get access. Again, that's all of that. So it's a whole can of worms that I might cover in a future video, but just know for now, Address Sanitizer, you can see, catches it before the operating system does. And yeah, once again, to fix this bug, we just go down here and we'll just make the buffer bigger. So we'll just make it, for example, right now there is 9 of them in here. So we'll make the buffer 11, but then we'll also make this 10 so that it's actually 0 indexed and stuff like that. And then finally, I'm just gonna add a new line so we can print this. So now we're gonna compile one last time with Address Sanitizer and see if it kind of yells at us. So if it doesn't, that means our program is perfectly fine. And there we go. It is perfectly fine. Everything printed it. And by the way, let me just actually take out this warning flag as well, because this is a bad practice. I just put it in for this video just so that it doesn't spoil the errors. But no warnings and Address Sanitizer doesn't yell. So that means our program is alive and well. So there we go. That is the end of this video. Hopefully you enjoyed. Please leave a like and subscribe. And yeah, I will catch you in the next one.